Okay, so here's a lecture for section 15.3. We'll talk about a little introduction to doing double integrals in polar coordinates. So the reason why we want to talk about polar coordinates is if I have a double integral given to me on a region over a disk, let's see how this would set up in just rectangular, what we've done so far. If I draw the region out, I'm going to have a circle filled in. My x values go from -2 to 2. My y values are from -2 to 2. So I can break this up. I can bound my y values. So when I write my double integral, or my iterated integral, my x values go from -2 to 2. My y values go from negative square root of 4 minus x squared to positive square root of 4 minus x squared. So a couple things to think about here. These are my y values, these are my x values. It might be helpful if you put a little variable here to remind you which one's which. Because here, since I'm doing y first, my dy needs to come first. X is the first integral on the far left, so that means that dx needs to be my differential on the far right. The issue that we have here is this might make our integration, our second integration in terms of x, very difficult, harder than maybe we want to do. So this is going to give us the idea or make us want to find another way to write the integral. So that's why we want to look at polar coordinates. So reminders. So x is equal to r cosine of theta, y is equal to r sine of theta, and I have the relationship that x squared plus y squared equals r squared. So what that does for my region, this is going to turn into r squared is less than or equal to 4. So that means r is less than or equal to 2. So I can write my bounds for that region as 0 is less than or equal to r is less than or equal to 2, and then 0 is less than or equal to theta is less than or equal to 2 pi. So if I'm going to write this out, from 0 to 2, that's for r. The integral from 0 to 2 pi, that's for theta. And my function, instead of x, I'm going to replace all my x's with r cosine of theta. I'm going to replace all my y's with r sine of theta. Now what we have to figure out is what's my relationship going to be for dA? So just real quick reminder. When we did this at the beginning in 15.1 and 15.2, I had some region in my rectangular coordinates in the regular Euclidean plane. Oops, I don't want those. And then we broke it up to look at different rectangles. So my dA represented the area, was the area of that rectangle. And as I added all of them up, I wanted the dA of that area to get smaller, smaller, and smaller. So I took more and more and more rectangles, right? So this was, that area was I could write it either way, because I have the commutative property for multiplication, right? That was called Fubini's theorem. Which says when I iterate my integral in 2 dimensions, it doesn't matter if I take the dx dy or if I do dy dx. Keep this in mind because sometimes the function or the surface that you have, it's going to be much easier to integrate y values first. Sometimes it's going to be easier to integrate x values first. So make sure you're paying attention to how the function, how everything works. When I look at this in polar, our coordinate plane is set up slightly different. So I have, these are going to be changes in theta. These are changes in my radius. So what I'm looking at here, the rectangles, so to speak, have a little bit of a curve to them. So to talk about dA, well, dA just means the area of this rectangle as I get really, 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 really small. I know it's not really a rectangle because it has a curved sides. These two are straight, but they're not parallel. I'm going to say rectangle though, because we're going to look at as the number of these get really, 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 really big. So that means all of these rectangles are going to be getting really small to the point where I can say that that's about equal to a regular rectangle. So when it's about equal to, we said that these dimensions here, this is going to be a dr, because that's the change of radius, how my radius is changing. This side right here, that's an arc length, because it's a part of a circle. So the way we find arc length, well, the entire circumference of a circle is 2 pi r, and I want to look at a piece of it. So that's how much of the part of the circle that I want. So these two are going to cancel out, and I'm left with this measurement when they're really, really, really small is r times d theta. So the area of this rectangle is going to be r times dr d theta. Keep in mind, this is not a super rigorous proof. This is just an introduction so that you can understand what the idea is and what the relationship is so that we can rewrite our double integrals in terms of a radius and an angle instead of in terms of an x and a y value. When we go to chapter 15.9, the end of this chapter, the last unit is on change of variables. So we'll talk about the Jacobian, which is a more rigorous way of defining what happens when I change from one set of variables to another set of variables. So we'll look at that in 15.9. The Jacobian is what tells us this r value right here. So that means in polar coordinates, our double integral, we can rewrite this as, so this will be from my theta, my angles, my r value will go from a to b. That's f of r cosine theta, r sine theta. Then I have r dr d theta. So now here, when I do this, one thing to keep in mind, do not forget that r. One of the biggest, most common mistakes is you're going to forget the r when you're rewriting the integral. Second thing to notice is I'm writing the dr first and I'm putting the theta second. We do that because typically if I have a function, it's r equals some function of theta. So that allows us to extend to say like, well, what if I don't just have r equals some constant? What if r is equal to a function? So that allows me to say that I can have from one function of theta to another function of theta. And then this would be from alpha to beta. So here, this is on what's called a polar rectangle. That's similar to a rectangular system where my x values went from a constant to a constant and y values went from a constant to a constant. If I'm integrating over a circle or a disk, centered at the origin, I have what's called a polar rectangle. That would be this here. But then this extends the same thing that we did in 15.2, where I was able to do integrated integrals, but I had a function at the first part of it, and then I had constants for my second integral. So I'm able to do this in polar 2. That's an introduction. What I'll do now is I'll make a couple of videos to work out some problems, some examples. And then feel free to use the discussion boards to help each other out. I'll go ahead and answer discussion questions also. Thank you.